Continuing on, let's continue our discussion of real gases, liquids, and solids. Let's talk about phase diagram now. A phase diagram is a diagram that shows the stable phases of a pure substance or a mixture under various conditions and compositions. So for a one-component system, if we're just dealing with one pure substance, okay, a phase diagram for that can be represented by a chart or a graph that has pressure on one axis and temperature on another axis. Okay, you might have the graph might be shown as not log of pressure or log of temperature, but basically you have a diagram that where you specify the conditions by just specifying the temperature and the pressure. Okay, so common features. A typical phase diagram is sketched like this. Common features of a phase diagram for our pure substance looks like this. Okay, it's divided into four regions, actually, at least three regions. Here at low pressure, high temperature, these represent any point on this diagram in this region represents a condition where you expect to find your substance in the gaseous form. Okay. What happens if you were to raise the pressure of a gas at constant temperature? Eventually, what happens is it turns into a liquid. Okay, so the boundary between these two regions right here, this blue curve right here, the boundary here, each point on that boundary represents the point where your liquid and your gas coexist. Okay, so in other words, this blue curve right here is really nothing more than a plot of this blue curve. It's really a plot of vapor pressure of a liquid versus the temperature. Okay, so in the case of water, okay, in the case of water, if this was 1 atmosphere, what would this temperature be for water? At what temperature does the vapor pressure of water reach 1 atmosphere? 100 degrees Celsius. That's when water boils. Okay, so that's what you have there. Now, what would happen if you have a liquid? So this point right here is in the liquid region. That represents a condition. The pressure and the temperature at that condition, at that point, represents a condition where you expect to find your substance in a liquid form. What would happen if you were to cool that liquid, maintaining the pressure? Eventually what happens? So cooling means lowering the temperature, right? Eventually what happens to it? Solidifies. Okay, it freezes. So this point right here on the green curve, so this green curve represents what? The boundary between the solid and the liquid region. That represents conditions where you expect to find liquid and solid. So this green curve right here is what you would call, which I've already overwritten with the red curve. This green curve right here is what you would call your solid, liquid coexistence curve. Okay, those are conditions where your solid and liquid coexist. So this tells you how, you can say this tells you how the melting point or the freezing point depends on pressure. You exert a higher pressure on your liquid here or your solid, you increase your melting point or your freezing point. Okay? Now, typically this curve right here leans this way, okay? Leans to the right, but water is an exception in that in the case of water, this curve actually leans to the left. So in the case of water, if you raise the pressure of water, 1 atmosphere for water, okay, would have a melting point of what? What's the melting point of water? 0 degrees Celsius. Now, if you were to raise the pressure on the water, on the ice, you would actually be able to get it to melt, lower the melting point, okay, slightly. This is a very steep curve, so there's just a very slight change in the melting point if you increase the pressure on the ice. So that's one explanation why if you were to skate over ice, okay, you're putting all your weight on that little tiny blade. Okay, so you're putting a lot of pressure on the ice that gets the ice to melt under you. That's what allows you to skate over ice. Okay, but dry ice would have this, the solid liquid coexistence curve for dry ice would look something like this. So if you were to skate over dry ice, the increased pressure would just increase the melting point of the ice, so the dry ice is not going to melt under you. Okay. Now down here, what do you have here? Based on the information I've given so far, this red curve right here is what you would call your solid vapor coexistence curve. Okay, that's a sublimation temperature versus pressure, or you can say that's the vapor pressure of the solid versus temperature. Okay, so that point, that curve right there. So if I have, let's just say, in the case of carbon dioxide, actually, 1 atmosphere is down here. So if we have solid carbon dioxide, okay, if I were to warm it up, okay, increase its temperature without changing the pressure, it will automatically directly turn from a solid into a gas without melting. So that's what happens to dry ice. In the case of water, 1 atmosphere would be somewhere up here. So in the case of water, if I were to heat up my water at 1 atmosphere pressure, it will first turn into a liquid. If I keep heating it, eventually it turns into a gas. Okay? Now, this point right here, down here, labeled TP, that's called your triple point. It's characteristic of a substance. It's very well defined for a given substance. It's a unique identifying property for a substance. So water has a well-defined triple point of, let me see what the triple point of water is. I think I might have it here. Let's see. We can look up triple point of water. I think it's 0.006 atmosphere. Triple point of water is 0.01 degrees Celsius, but what's the triple point pressure? Let me see. I think that's 0.006 atmosphere. Yes. Yeah, it's 0.006 atmospheres. Okay, so this is the triple point of water. This temperature, the temperature at the triple point of water is 0.01 degrees Celsius. So that's 0.01 degrees above its normal melting point. Okay, so in the case of water, okay, the normal melting point, like I said, in the case of water, this curve is actually leaning this way. At 1 atmosphere, okay, at 1 atmosphere, the melting point is 0 degrees Celsius. And at 0.006 atmosphere, so this is 1 atmosphere, and 0.006 atmosphere, that's your triple point right there. That temperature right there is 0.01 degrees Celsius. So that's characteristic of water. Yes?
Is that say in a vacuum or in boiler?
Oh, yes. That's this curve right here. Like if you were to lower, if you pull a vacuum on your water, right? Like let's say this is 1 atmosphere. The vapor pressure of water at 1 atmosphere. Vapor pressure of water reaches 1 atmosphere at 100 degrees Celsius, right? If you pull a vacuum above your water, you can get it to boil at a lower pressure, at a lower temperature. So if you lower the vapor pressure, the pressure above it, then it will boil at a lower temperature. Okay? So not only is this a function of vapor pressure versus temperature, you can also think of this curve, this liquid vapor coexistence curve. You can also think of it as boiling point versus pressure. Okay? So that's triple point. Triple point means that's a condition where you expect to find solid, liquid, and gas all at the same time at equilibrium. Okay. Now, CP here, what does CP stand for? What do you think it stands for? Critical point, right? CP stands for critical point. That's beyond that temperature, you can no longer liquefy your gas. And so beyond this region right here, SCF, is what is a region where you would have what's called a supercritical fluid. Critical fluid. Right? So that's a diagram that summarizes conditions where you would find stable phases of water. Okay, you'll notice. Okay, this is really a very simplified diagram. The one I've shown you earlier on the website. This is a more realistic depiction of the phase diagram. Okay, so that's your. So those are not really straight lines. Okay. All right. So let's look at this diagram right here. And 1 atmosphere, does a substance represented in this diagram sublime or not? Yes or no? A, yes. B, no. Oops, I lost my clicker. What happened? At 1 atmosphere pressure, does the substance represented in the diagram here sublime or not? What is sublimation? Changing directly from solid to a gas without melting into a liquid first. A, yes. B, no. So here you have at room temperature, 1 atmosphere, this is typical ordinary room conditions, right? So if I were to heat my sample, what's going to happen? It's going to cross over from the solid region to the liquid region. It's going to melt first. I keep heating it. It will start to boil when it reaches T1. So what is this T1 right here? This is what you would call your boiling point, right? This is where your where your liquid boils. This is your melting point right here. Okay. So in other words, under what conditions will a substance sublime under ordinary conditions? It would sublime if the triple point happens to be above 1 atmosphere. If the triple point is below 1 atmosphere, it will not sublime by heating at constant pressure. So why does food cook faster in a pressure cooker? What happens in a pressure cooker? You increase the temperature, right? You're going to have liquid, water, and water vapor, right? Liquid and gas. You increase the pressure. So if you increase the pressure, what happens to the temperature of your water and your liquid and your gas? So if you increase the pressure, the temperature increases. Okay? You're able to achieve a higher temperature for water in a pressure cooker. Now, those are just the basic features, common features you'll see in a phase diagram. Phase diagrams can also show other solid phases, multiple solid phases, because substances are known to exist in more than one solid form. Okay, so if this is this represents a gas, right? This region, and this region represents a liquid. Okay, this would have to be a solid, right? If you see that extra boundary there, that means there's another solid phase there. So a solid can undergo transformation from one crystalline form into another crystalline form. So you could have multiple solid phases in a phase diagram. So what would what would be this point A? What would this point A represent? That would be a condition where you would find two forms of the solid in equilibrium. Okay, what would point B represent? solid and liquid at equilibrium. Point E would represent liquid and gas. Point E would represent triple point where you have solid, liquid, and gas. Point D would represent another triple point, but this time you have two solids in equilibrium with the gas. Okay? I guess there's no point F there. So here's example. This is a phase diagram for mercury iodide looks like this. This is just an illustration. This is not drawn to scale. What phase is represented by point D? Solid, liquid, or gas? Let's make that a clicker question. Point D is what? A, solid, liquid, or gas? Solid, B, liquid, or C, gas? Point D represents gas. Very good. What about point C? Does it represent solid, liquid, or gas? Liquid, very good. Point B, solid, liquid, or gas? That would be a solid. Okay. And point A, solid, liquid, or gas? Also a solid. Okay. Now, according to this question, so A is a solid phase, represents a solid phase. Region B represents a solid phase. Solid mercury iodide is known to be red at room temperature and turns yellow. It's still a solid. It turns into a yellow solid when heated to 127 degrees. Which region of the phase diagram represents solid mercury iodide that is red? Is it A or B? Okay. It's red at room temperature. It's a red solid at room temperature. It becomes a yellow solid at 127 degrees. It's mercury iodide in both cases, just different crystalline forms or different colors. Which region of the phase diagram, A or B, represents solid mercury iodide that is red? What's room temperature? 25 degrees Celsius. And so you heat it to 127. So if you have to heat something, what happens to the temperature? Increase, right? So you have to go to the right. So red when it's in region A. When it switches over to region B, you heat it enough, raise its temperature enough, switches over to region B, it becomes a yellow solid. And if you keep heating it, what happens to it? Eventually it melts, right? If you keep heating it, eventually it melts, turns into a liquid. If you keep heating it, eventually it turns into a gas. Right. Let's talk about energy changes associated with phase changes based on a phase diagram. Consider the substance given here with this phase diagram. What information do you need to calculate the heat that you need from point A, from state A to state B, state C? What information do you need to determine how much heat is it going to take to bring it from temperature TA to temperature TB? You remember the formula? Q for no phase change, just temperature change, would just be equal to 1. It's a formula for Q if the only thing happening is a temperature change. C delta T, right? C of the solid. What is C? What do you call C? Heat capacity, right? Of course, chances are if you look that up, it's given to you per mole, so you have to multiply the per mole value by the actual number of moles. Okay. Now, from point B, what happens from point B at point B? It turns from a solid to a gas, right? So, what happens then? So, this is Q for heating from TA to TB, right? So, this delta T would be TB minus TA. At point B, what happens to it? Q for the second leg of your second step in your process would be what? Changing from a solid to a gas, what happens? What's your Q there? What information do you need to look up? You need to look up the delta H of sublimation. Okay? Delta H sublimation, and that might be given to you on a per mole or per gram basis, so you have to multiply it by the actual number of moles or amount in grams. So that's the second step. What's the third step here? In the third step, you're going to raise the temperature from TB to TC. Okay, once you go from TB to TC, what's the form of your substance now? It's now a gas, right? So you need the heat capacity of the gas times delta T. And again, heat capacity might be given per mole or per gram, so you multiply it by the actual moles or grams. Right? What would Q versus T look like? Amount of heat versus temperature. I start off at T sub A. Okay, I'm going to start at T sub A. Okay, what will happen when I go to T sub B? The higher the temperature, the more heat I put in, the higher the temperature, right? What happens if I keep heating at temperature B? So this is going to be, this difference right here is Q1. What happens at temperature T sub B? It will sublime, right? While it's subliming, the temperature will remain constant. So temperature constant means you get a vertical line, right? So this amount right here, Q2, is the delta H of sublimation. And what happens when the gas has been the solid has been transformed into a gas completely? Keep heating it, temperature will start going up again. Okay, so this difference right here is Q3. Okay, should be able to do a curve like this. This is called a heating curve, right? For a substance that sublimes. Okay, what would it be if it were over here? Then you're going to have the heat of fusion, delta H of fusion, and then you have to have delta H vaporization. Okay. Now, what if I were to plot temperature versus Q instead? What would it look like? Temperature TA is going to go to temperature TB, right? And then what happens? You keep heating it, the temperature remains constant while it's subliming. This is sublimation right here. Okay, let's see. So this one right here we say is Q1. And this thing right here would be Q2, delta H sublimation. And then once everything's turned into a gas, the temperature goes up again. Q right here is going to be equal to Q3. Okay? So Q1, Q2, and Q3 are the heat amounts of heat that you need to supply for this process to occur. Okay. The slope of these curves right here, these coexistence curves, depend on delta H and delta V. Delta H, okay, what do you know about delta H? From solid to liquid, what's your delta H? That's fusion, right? Solid to liquid, is it exothermic or endothermic? When you're melting something, do you supply heat or remove heat? You're supplying heat, so endo. Heat has to go into your system in order to melt, right? Generally, when a solid melts, what happens to the volume? Does it expand or contract? When a solid melts, it expands. So delta V is positive. So dP dt, that's basically delta P over delta T. That's the slope, okay, is a positive number for this freezing line, okay? So that's why it's leaning that way. Why is it leaning the other way for water? For water, it actually leans the other way. The slope for water, delta P over delta T, is negative. Why is that? The reason is delta H is still positive, but your delta V, what happens to ice when it melts? Ice actually shrinks when it melts, right? So delta V is negative. Here, if you have a glass of water, fill it to the rim with water and ice. What happens when the ice melts? Will the water overflow? No, because the ice shrinks when it melts. So delta V, the volume drops when ice melts. Okay, so delta H over T delta V, which is the slope, is going to be a negative slope, so it's going to lean this way. So water is the exception. Most solids will expand when you melt them. Okay? Now, why is the slope much steeper for this as opposed to this? The slope of your curve, delta H over T delta V, right? It's steeper for solid going to liquid because your delta V is going to be a very small number. Okay? There's not much of a change in volume when you're going from a solid to a liquid. So a very small denominator would make the whole fraction a much bigger number. So that's a very steep, this is very steep, right? You'll notice this is a very steep curve. Whereas this one is less steep. You have a big change in volume as you go from a solid to a gas or a liquid to a gas. Delta V is going to be a very big number. So that makes your slope very small. So that curve right there is not as steep. Okay? Now your solid gas line is steeper than the liquid gas line. That has to do with the delta H. It takes more energy to change generally from solid to gas than from liquid to gas. So delta H tends to be larger for sublimation than vaporization. So this is steeper than that one. The Clapeyron equation, oops. Oh, by the way, this equation that we had here, shown here, is a Clapeyron equation. So it summarizes, it's an equation that summarizes the behavior of these two-phase coexistence curves, these boundaries between your solid, liquid, and gas regions. Okay. Here's an application. Mentioned this earlier already. Explain why ice melts under an ice skater's blades. Okay, so this is 0 degrees Celsius, so this is not 298. Okay, so this is 273 Kelvin. Okay, melting point of water. Okay, melting point of ice. What happens if you increase the pressure? You lower the melting point of your ice, and so if you're standing on ice skates, you're putting all of your weight over that little thin blade. You're putting a lot of pressure on the ice to get the ice to melt under you. Okay. Now, the Clausius-Clapeyron equation is a modification of the Clapeyron equation, which takes into account the fact that the volume of a gas, when a solid or liquid turns into a gas, the volume of the gas is much larger than the volume of the solid or liquid. Okay? So, in other words, your delta V in the calculation of the slope is approximately equal to the volume of the gas, because you can ignore the volume of the liquid or the solid compared to the gas. Let's clarify that. Remember 1 mole of water. How many grams is a mole of water? 1 mole of water. So how many grams? Remember? 18 grams, about 18 grams. So how many mils would that be? Liquid water. What's the density of liquid water? 1 gram per mil. So that's about 18 milliliters, right? But that's if that's a liquid, right? Now, if you turn your water from liquid to vapor, water vapor, gaseous water, 1 mole of a gas would have a volume of how much at STP? 22.4 liters per mole, right? That's 22,400 milliliters. How does 22,400 compare to 18? Much bigger, right? In fact, if you only have 3 sig figs, 18 is not going to matter. It's like a drop in a bucket, right? So your volume changes a lot when you turn your liquid or solid into a gas. And so that equation that we had earlier can be simplified into this form right here. So this is the equation that describes, okay, remember your phase diagram? This equation right here describes this curve right here and that curve right here. This delta H for this curve will be delta H of vaporization, and for this curve down here, your delta H would be delta H of sublimation. Okay? So any 2 points on the curve, natural log of pressure on point 1 over the pressure at point 2 would be equal to negative delta H over R times 1 over T1 minus 1 over T2. So this is just an equation that describes this curve right here. So this will allow us to actually do some calculations, like how much does the vapor pressure change if you change the temperature, okay, or how much does the boiling point change if you change the pressure. Okay, so here's an example. Estimate the pressure inside a pressure cooker when the water temperature is 121 degrees. Delta H vaporization of water is 40.7 kilojoules per mole. So you use the Clausius-Clapeyron equation here, okay? So you're looking at this point right here. So at 1 atmosphere, we say water boils at what temperature? 100 degrees Celsius, right? That's 373 Kelvin. Now, if you want your water to boil at 121, okay, 121 degrees Celsius, what would that pressure be? Okay, that would be the pressure you need in your pressure cooker. So, how would we solve for this? We say ln of P1 over P2 equals negative delta H of vaporization over R, 1 over T1 minus 1 over T2. Okay? So what numbers do I plug in here? I can say that when T2 is 373 Kelvin, my pressure is 1 atmosphere. Okay? And so the question is, if T1 is, what's 121 Celsius? What's that in Kelvin? 121 plus 273, 394. So if T1 is 394 Kelvin, what is P1? Okay, and I'm given the delta H vaporization is 40.7 kilojoules per mole. Okay, so I know everything here. I can solve for P1. R, what's the value of R? For consistency, since my unit here is kilojoules per mole, I have to write my R in kilojoules per mole. R is 8.314 joules per Kelvin per mole. So, okay, for consistency, what I need, I'll change this to joules. So, 40.7 times 10 to the third joules per mole. And R is 8.314 joules per Kelvin per mole. Okay, so you plug those in, you'll be able to solve for P1. How would I solve for P1? I'm going to say ln of P1 minus ln of P2. Remember this identity from math? Ln of x over y is the same thing as ln of x minus ln of y. Okay, so ln of P1 minus ln of P2 equals negative delta H over R, 1 over T1 minus 1 over T2. Now, I know this number. I can just plug in all the numbers I need there, right? So what would that number be? Negative 40.7 times 10 to the third joules per mole over 8.314 joules per Kelvin per mole. So moles, joules per mole cancels out. So that gives you Kelvin times 1 over 394 Kelvin minus 1 over 373 Kelvin. So your Kelvin will cancel out. So that's ln of P1 minus ln of P2. What would that be? Okay. 1 divided by 394 minus, open parenthesis, 1 divided by 373, close parenthesis, equals, times 40.7 times 10 to the negative, 10 to the third, divided by 8.314. That's negative times negative, so that becomes positive 0.6995. Okay, so that's ln P1 minus ln of 1. What's ln of 1? Or here, let's just make that ln of P1 over 1 atmosphere. Okay, it's equal to that. So you can say then that P1 over P2, which is 1 atmosphere, is equal to 0.6995. Oops, sorry. Take the inverse log, right? So e to the 0.6995. So that would be 0.6995 inverse log. So inverse e to the x, that's 2.012, 2.013. And so P1 is equal to 2.01 atmospheres. Okay? So that's assuming I got all my numbers right. You see, you expect the pressure to be higher inside the pressure cooker. Okay, let me just verify those numbers for you. Okay, 1 divided by 394 minus, open parenthesis, 1 divided by 373, close parenthesis, equals that times 40,700 divided by 8.314. Yeah, negative times negative 1, and then inverse log. Okay. Okay. Solids, we're going to talk about that next time.